So the learning target here for this section is to use growth rates to identify the end behavior model of different functions. So a growth rate here is referring to how fast something grows as x approaches infinity. So there's a little acronym that we're going to learn here, which is n to the nth is the fastest, and then factorials, which is like x, remember with exclamation point. Then exponential functions come next, polynomials, logarithms, and then constants. Okay. So this is full, which is kind of a silly thing to think about, but fletful. Let me see if I can refocus this for you. Let me try this real quick. There we go. So n to the nth. This looks like something like this. 3, say I have x to the x. That would be an example of a variable to a variable. Or if I have 3x to an additional x. Or something like 2x to the x. Factorials would be x, or you could say 2 times x factorial. Okay, exponents, they would be something like 3 to the x. Okay. Or if I had like 1/5 to the negative x, you could rewrite that as 5 to the positive x, and so that would also be an exponential that's going to grow really, really fast. You could also do something like 1/2 to the x, and that's going to grow really fast as you go to negative infinity, but it's going to get really small as you go to positive infinity. So they're going to grow really big in this direction. Polynomials, we've been looking at polynomials forever, where you have x to some number. Okay. So that could be x cubed, it could be x to the first, that would be a linear. This may also include square roots. So that would be x to the 1/2 or to the 1/3 or anything to a fractional exponent. And as this number here gets bigger, it grows faster. Bigger grows faster. Logarithms, we haven't spent very much time talking about logarithms, that's our next unit, but a logarithm would be something with it usually says log, like log base 2 of x. That would be an example of logarithms. You probably won't see any of those today or in our regular in-class practice, but we might touch on them briefly. The other way you might see log is there's something that looks like this, ln. It's probably a button you've seen on your calculator a whole bunch of times, and this is a special kind of log. Constants don't grow at all, so those would be numbers like 3, 5, -15, anything that's just a number. So we're going to use this model to help us talk about end behavior. So these are the fastest on this side and slowest on this side. So there's a continuum here from fast to slow. Okay, so we're going to find the right and left end behavior models for each of the following. So right end, so as x goes to positive infinity, which one of these guys has more weight? Well, this guy right here is going to grow exponentially as you go to the right and shrink, decay as you go to the left. So which one of these guys is going to have more power? It will be this guy, e to the x. So notes to remember for that one, e to the x grows as x approaches positive infinity. Okay? The left end, which means x is approaching negative infinity, well, this guy's getting closer and closer to 0 as you go to negative infinity, so he becomes basically a non-entity as you go to 0. So that means that this guy has all the weight on the left. Okay. So that means that we're going to be looking at a function that looks almost exactly like y equals x on the left. X outpaces or has more weight as x approaches negative infinity. So this x is representative of this x. Let's look at this guy. So we have an exponential, we have a polynomial, and we have a log. So as x goes to positive infinity, which guy is going to have the most weight? So we come back up here. Well, it would be e, non-flippable. So this would be this guy having the most weight. So as x approaches positive infinity, this guy is going to carry the most weight, so it's going to look mostly like this. We would have 2 to the x would be our model that has the most weight as you go to positive infinity. As you go to negative infinity, this is going to be a little bit different. Now we haven't really looked much at what this guy looks like at negative infinity, but logs, they are the inverse of exponential, so exponentials grow like this, so logs reflect over that. So these guys go to 0 on the left. Okay, so he becomes basically worth nothing on the left. He becomes basically worth nothing on the left. And so this guy is the only one that's going to have any weight as you go to the left. So it would be that negative 3x to the 5th. Notes to remember: natural logs or logs of any type are going to grow slow as x goes to positive infinity and go to 0 as x approaches negative infinity. In fact, it has some domain constraints, but we'll look at that later. Okay, this guy right here, we've got x approaching positive infinity. So this one right here can be a little confusing. So 3 to the negative x is the same thing as 1/3 to the positive x. So what would that look like? If I just were looking at this guy, it would get really big as x approaches negative infinity, and it's going to go to 0 as x approaches positive infinity. So the right-hand model, this guy has like no weight on him. He's going to 0. So that means this guy is going to be our outpacer on the right. So x cubed wins the race as you go to positive infinity. But as you go to negative infinity, you go off this direction. This guy has way more weight because it's an exponential. So this guy is going to outpace on the left. So x 1/3, or you can write it as negative 1/3. I'm sorry, 3 to the negative x. Notes here: 0, 1. If we have a base, so the exponential function's base, we're going to grow on left, or as x approaches negative infinity. So we're going to look at these practice questions in class. Give them a shot. I want you to choose the best answer. And I don't know why I can't spell. Answer. There we go. So which of the following functions grows faster than e to the x? So come back up here and use your model. As x goes to positive infinity, choose which one is going to outpace it. Which two functions grow at different rates? Okay. Which of the following grows faster than this natural log raised to an x? This one's kind of tricky because we haven't looked much at logs. There's log rules involved here. So we go over that in class, but it's not a super big deal if that one is a struggle. And then this one down here, we will review in class, but take a stab at. So describe the method you use to identify n behavior models of functions. Explain how the n behavior models for an exponential function are different than other functions. So what things do I need to know when thinking about exponential functions when doing n behavior versus other functions?